Hi everyone. In the previous lectures on the series of lectures on RF system design, we discussed about the conventional amplitude modulation. We said information can be transmitted in free space by modulating or changing the amplitude of a carrier signal as shown here. Now I have already explained this term. I said AC here is the carrier amplitude, mu here is the modulation index, which is the ratio of the maximum excursion in the message signal, max of m of t upon AC. So it tells you how much modulation index tells you how much the message signal varies with respect to the carrier amplitude. And m hat of t here represents the normalized message signal, which is the message signal normalized to the maximum value of the message signal, m of t upon max of m of t. Now given this, we discussed we discussed the signal in time domain. We spoke about what is the total power contained in the signal, and we also spoke about how that power is distributed as a function of frequency in the frequency domain. So that's what I've shown here, the distribution of the power, in fact the Fourier transform of a message signal. So here we have a low frequency message signal. Again, it's a real message signal, so therefore they will exhibit conjugate symmetry, meaning at any given frequency f and its equal and negative frequency, the Fourier transform will form a conjugate pair. The Fourier transform will be conjugate of each other. So in case of amplitude modulation, we simply multiply it with a carrier signal, so the same thing gets translated to higher frequency fc as shown here. Now in addition to the message signal, there is also a carrier present, and that's what we called it as a conventional amplitude modulation. And the carrier power, I'm directly showing the power spectral density, I'm calling it PC, which is AC squared by 2. That's your carrier power. So half the power will be in the positive frequency, half will be in the negative frequency. So PC by 2 will be in the positive frequencies. So the weight of this impulse here at the carrier frequency is PC by 2. Now this message signal power, we calculated the message signal power in the previous lecture. We'll have to square this and find it out. So it will turn out to be mu square AC square by 2 into PM. So PM is the normalized message signals power. So that's the total signal power which I've written here. I'm going to write AC square by 2 as PC. Then the total signal power is given by PC PM into mu square. This is the total power contained in the signal. Now half of it will be in the positive frequencies, half of it will be in the negative frequencies. So this is the, to be clear, when I say P signal, I am referring to the RF signal, not the low frequency. This is upconverted signals frequency, excluding the carrier part. Okay, so this will be, half of it will be distributed in the positive and half in the negative. So if you see, these two band of frequencies will contain half of this power. So it will be PC PM mu square by 2. So that will be the power. PC PM mu square by 2 will be the total power in the positive frequencies, out of which half of it will be in the upper sideband and the remaining half will be in the lower sideband. So upper and lower sidebands are simply the positive and negative frequencies at the lower frequency. When they get upconverted, the positive band of frequencies become the upper sideband, frequencies greater than Fc, and the negative band of frequencies become the lower sideband. So again, they form the conjugate symmetry here. So if you move fx units from Fc in either directions, the Fourier transform at these 2 points will be complex conjugates of each other. Okay, so that total power, the sideband power, I'm using the term sideband. There are 4 sidebands here, including negative and positive frequencies, is PC PM into mu square by 4. Okay, so that's the power contained in each sideband. And this value PM, now we'll try to compare it with the carrier power. I've already done that in the previous lecture, but quickly I'll try to compare it with the carrier power. PM here is the normalized message signals power. So here, if I assume the message signal to be a sine wave, PM will be always, it will be half. And for most narrowband signals, power is concentrated on a very narrow range of frequencies. For those narrowband signals, PM will always be less than half. For example, if I consider a square pulse which goes from say +1 to -1, PM will be equal to 1, but that's a wideband signal. So that's why I'm making it clear that it's a narrowband signal. I can make this assumption that PM will be less than or equal to half. So your signal power, which is mu square Pc Pm, will always be less than mu square Pc by 2. So if I consider the positive frequencies, it will be less than mu square Pc by 4. Which again we can see, if your modulation index mu is less than 1, if we can see that it's much lower than, or rather it's lower than the carrier power. So that's one drawback of conventional modulation. We said we are spending a significant chunk of the transmitter power on transmitting the carrier. Okay, our intended signal which needed to be carried was the message signal, but your carrier power is almost 2x, we will see in a few moments, is 2x larger than the message signal. So that's why it's very inefficient. So quickly, again, just for the sake of completion, I'll very quickly talk about the sinusoidal modulation. What if your message signal is a sinusoid, how the Fourier transforms and power spectral density looks like, and we can quickly discuss efficiency from a frequency domain point of view as well. So let's assume the message signal here is a sinusoid with an amplitude AM. The normalized message signal will just be cos omega mt. Then the transmitted signal is going to be AC into 1 plus mu cos omega mt into cos omega ct. You can very easily, using some simple trigonometric algebra, split them into three sinusoids. One of frequency Fc, the other one of frequency Fc plus Fm, and Fc minus Fm. Okay, and the amplitude of the signal of frequency Fc is AC. The amplitude of this guy is going to be mu AC by 2, and Fc minus Fm is also mu AC by 2. So you have three sinusoids with three different amplitudes. Three sinusoids, two of them will have similar amplitudes here, but frequencies are different. Now, to plot its Fourier transform, you just have to plot the Fourier transform of sinusoids. In this case, when you transmit cos omega m and cos omega ct, both the carrier and the message signal are in phase, you will get it's purely cosine signals. So you can plot for Fc, you can see the signal amplitude, half the amplitude is on the positive and half on the negative side. So you have to construct a cosine cos omega ct using two complex exponentials with half the amplitude of the sine wave. So that's where you see two impulses with weights of same weights but half the amplitude weights. And the other two side bands, if you see now, these are sinusoids, so they'll be impulses, the side bands will be impulses. All the power will be just lumped onto one single frequency of value Fc plus Fm or Fc minus Fm. The amplitude here will be half of this amplitude, which is mu AC by 4, and the remaining half will be on the negative frequency. And the same holds true for the lower sideband as well. Now quickly we can look at the power spectral density. Just one point to remember here is that I've assumed these two signals to be in phase. They need not be in phase. They can be sine omega m and cos omega t, or cos omega m and sine omega t. In that case, the phases will keep differing. The Fourier transform, these two sideband phases will be different. Here they both are in phase because I've assumed cos and cos. Otherwise the phase will be different, but the amplitudes, the frequencies, they will all remain the same. Only the phase terms will differ, but since they are all real signals, they exhibit at lower frequency they will exhibit conjugate symmetry. So which means the positive and negative frequencies will be conjugate pairs. Therefore at higher frequency, when you upconvert it, the same condition holds true. So these two frequencies will be complex conjugates of each other. So that is something that will hold true. Okay. But power spectral density, when you talk about power spectral density, we don't have to worry about the phase. That's going to be the same irrespective of the phase of the message and the carrier signal. And I'm writing the power spectral density here. I've assumed a sinusoidal modulation. So square the individual terms. The power contained in the carrier, I'm talking only about the positive frequencies now, will be AC square by 4, which is PC by 2, half the power in positive frequencies. Similarly, the upper sideband power is going to be mu AC square by 16, which can be written as mu square PC upon 8, and lower sideband will also be mu square PC upon 8. So if I assume the maximum modulation index, which we will see will be always less than or equal to 1 in conventional AM, if I assume mu to be equal to 1, the carrier power to the sideband power. So the sideband here, I'm talking about, let's say, upper sideband. The upper sideband power is mu square PC by 8. If I assume mu to be 1, it will be PC by 8. So the maximum sideband, upper sideband power is PC by 8. And the carrier power is PC by 2. I'm talking only about the positive frequencies. If you see, the upper sideband power is 4 times lower than the carrier power. Or in decibels, I can call it as 10 log of 4 will be 6 decibels. So your upper sideband power is 6 decibels lower than the carrier power. And same thing holds true for lower sideband. It will be 6 decibels lower than the carrier power. So I thought it's better to know the distribution of power, especially in sinusoidal modulation. It will be 6 decibels lower. The upper or the lower sideband will be 6 decibel lower. When you add the two powers, the total sideband powers will be PC by 4, and that's going to be 3 decibels, half. It will be half of the carrier power, so it will be 3 decibels lower. So therefore the efficiency we can directly compute from this graph itself. The total signal power is, I'm talking only about the positive frequencies here. Ideally I can multiply into 2, I will get negative frequency power, total power then. So PC by 4 is the total sideband power divided by PC by 2 plus PC by 4, and we get the term 1/3. So the maximum efficiency, the transmission efficiency is 33%. So mind you, when we talk about transmitter efficiency, generally in today's times, when we talk about IC design, we talk about what is the total power transmitted to the delivered to the antenna, and compare it with the total power dissipated or drawn from some power supply source. So that's the efficiency we talk about. But here what I'm talking about is the transmission efficiency. Now this is the total power the antenna is radiating. Out of the total power it is radiating, only a small fraction of it, in fact 1/3 of it here, is what is useful power. The remaining 66.67 power, 66.67% of that power is just carrier power. It doesn't contain any information. So that's what this result is telling us. So now we'll see how to build a receiver for this, and why is this condition, the modulation index being less than or equal to 1, should hold true. Why do we need to ensure this condition? That will become clear in a few moments once we start discussing the receivers, the first generation radio receivers. So our goal here, I've just drawn, let's assume your message signal looks like this. The AM signal will look something like this. The amplitude of the carrier is going to vary. We need to design an extremely simple circuit. So keep in mind, this is the first generation radios. Electronics had not evolved yet to so much. Vacuum tube amplifiers were just around the corner, were just been invented. We had, in fact, before that we had what we call a very crude metal semiconductor junctions, which were also used as radio receivers. We didn't have an understanding of the physics of the semiconductor device yet, but some devices were being in use. Okay, and the diode, the device that was being in use was a diode, where current can flow only in one direction. Now we'll see, we'll try to build a very simple receiver using this diode. Now if I take a diode and a capacitor circuit as shown here and pass a sine wave through that, initially let's assume this is at 0, a diode will conduct if there is a finite positive voltage across it. It should be in forward bias. So when the input voltage is increasing, the diode conducts, output voltage will follow the input. And when the input voltage reaches V peak, that's the maximum voltage of the input, your capacitor is also charged to V peak. At that point, your capacitor has a charge of Vp or volts, Vp volts across it. From then onwards, when your input decreases, when the input becomes lower than Vp, the diode will be cut off and there will be no path for the current. So now there is no path for the capacitor to charge or discharge. So capacitor will just hold its charge. So it will hold its voltage at V peak indefinitely. So now if you see, this circuit serves as a peak detector. Okay, so even though the idea is very old, it's even today in some fields called RF energy harvesting or energy detecting circuits, where you want to detect a narrow band energy present in a certain band, peak detector circuits still find some applications. So if I feed a sine wave, I've gotten a DC voltage at the output, and this DC voltage is indicative of the peak value of the input sine wave. But what we need a circuit which should be able to track the peak voltages. It should be able to track the envelope. So this is the envelope. The change in the amplitude is what I'm calling as envelope. We should be able to track that envelope Not the carrier frequency, not just the single peak, but it should be able to track it. So the other circuit, if for example, let's say I feed an amplitude modulated signal here to this circuit, a peak detector, it will keep charging. The diode will conduct till this point, it will keep charging till V peak. After that, your diode will always be reverse biased, because you can see in this waveform, the input voltage is always lower than V peak, so diode will always be reverse biased. So output will stay constantly at V peak itself. So yes, it's not serving as a good, I can't use this circuit as a envelope detector. I need the output of the capacitor also to change, so that it is able to detect the changes in the envelope or the amplitudes. Now let's take another extreme. Instead of capacitor, let's say I have a resistor. I have a resistor in place of a capacitor, and I'm going to feed a sine wave. Now since a diode, so the resistor, the other end of the resistor is at 0, if there is no charging current to the resistor, this node will be at 0 volts. Now for this diode to conduct, all you need is a positive voltage here. So if this node voltage is positive, diode will conduct. So, and in the positive half cycles, that condition always holds true, because your input will be connected at the one end of the diode and the other end is the resistor. And in the positive half cycles, diode will conduct and the output will simply be equal to the input. So here I'm assuming the diode has 0 cut-in voltage. So input and output are nearly the same. But in the negative half cycles, this node at this point, when your input goes to 0, output is also going to 0. After that, when your input goes through the negative cycle, the diode will be cut off and the resistor will always show 0 volts. So this circuit is called as a half-wave rectifier. It follows the input only for the full positive cycles. Now if I feed an amplitude modulated signal, a conventional amplitude modulated signal through this diode circuitry, what will happen is that I will only detect the positive peaks. I will detect this peak, and so on. So that's the waveform you will be getting out of it. And we don't want this as well. We don't want to detect the full sine wave. We don't want to detect the full sine wave. We only want to detect its amplitudes. Okay, so here we have two circuits. In the first circuit, we are only detecting the amplitude, and in the second circuit, we are only detecting the positive peaks. In fact, the entire positive waveforms, not just the peaks, but the entire waveform is being, that's the output of this circuit. So we need something in between. So that's when a circuit, we are just going to add the resistor and capacitor in parallel and have a diode in conjunction with it. So if I feed a circuit, a sine wave to this circuit, let's see what happens. So initially, of course, the same thing will hold true. If I assume this is 0 volts, the diode will conduct till V peak, and after that your capacitor has the capacity to hold its charge. Resistor didn't have that previously. So when your capacitor is at V peak, when the input reduces, the diode goes into cutoff region, and immediately the output will no longer stay at V peak, because the resistor in parallel, that will slowly start discharging the capacitor. So this is how the sine waves look. Your capacitor will slowly be discharged, and again when the input signal, because now the capacitor voltage is lower, when your input signal exceeds that discharged capacitor value, you will again track and the process continues. So now you have an interesting circuit. You are able to detect peaks. So if I take this circuit and feed a conventional AM signal to this, then I want to detect only the peaks. So two things has to be ensured here. So when you talk about an RC circuit, how fast it can discharge or charge is dependent on a parameter called time constant, which is simply given by the product of R into C. Now we need to detect the peaks. You need to detect the change in the peaks. So which means your RC time constant, how fast it's able to discharge or charge, that should be lower than the rate at which the peaks are changing, because you need to detect the peaks. So you should be able to track, the RC circuit should be able to track that. So the time constant here should be lower than this speed with which your envelope is changing or the message signal is changing. So let's assume your message signal is a pure sine wave of frequency FM. Then for a sinusoid, you can clearly show, let's assume A cos or A sin omega t, differentiate the signal. The maximum rate of change of the signal is simply given by A upon FM. This is a very trivial result. One can easily show, the maximum rate of change, I mean, it will be proportional. It can be 2 pi fm, A by omega c and all that. So it will be proportional to 1 by fm. So that's what I'm trying to come at here. The maximum rate at which the amplitude changes will be proportional to 1 by fm. So therefore your time constant, the time constant of your RC, because we want to track the message, that should be lower than 1 by fm. So this is a condition that you'll have to meet. Now, but how low can your time constant be? Can it be very low? I mean, can it be 0? But if it is 0, you will start tracking even the carrier frequency changes. You will start tracking the sine wave fully. Instead of the peaks alone, you will start tracking the sine wave fully, or at least the positive half cycles. You don't want that. You only want to track the peaks and not the carrier frequency. Carrier frequency is a signal which is changing at much faster rates. You don't want to track that. So you have to ensure your time constant is not able to track that. So which means your time constant has to be much greater than, which is RC here, has to be much greater than 1 by FC. So same way, if I assume the sinusoid to be a carrier of frequency FC, the rate at which the signal changes is proportional to 1 by FC. So your time constant has to be much larger so that you don't react to those changes in the carrier frequency. You only want to react to message signal frequency changes. So the condition turns out to be, you looked at the signal in time domain, RC should be much greater than 1 by FC. The other condition is the time constant should be low enough so that it's able to track the amplitudes. So RC should be less than 1 by FM. So the condition that we'll have to satisfy is 1 by FC. Your time constant here should be much greater than 1 by FC, because you don't want to track the carrier frequency at all. So carrier frequency is changing at much faster rate. You don't want to track this. You only want to track its peak. But your time constant should be greater than 1 by FC, but it should be less than 1 by FM. So if you satisfy these two conditions, you will be able to track the envelope. So this circuit, if you feed a sine wave, an amplitude modulated signal like this, the diode is going to conduct, it's going to discharge this way, again charge, discharge. So you will be able to detect the message signal approximately. So this RC time constant, the value of R and C, has to be chosen carefully so that you will be able to track the envelope but not the carrier. Okay, we can also look at it from frequency domain to easily understand. So if you see, since most of us by now would have done circuit design basic course on first order circuits and second order circuits, we can directly see that this RC circuit forms a low pass filter. And if this RC circuit has to pass the message signal, then the cutoff of the low pass signal, which is 1 by RC, should be greater than omega m or 2 pi fm. They should be greater than 2 pi fm if you want to pass the message signal. At the same time, you don't want to pass the carrier signal, which is a very high frequency. So therefore 1 by RC should be much less than omega c. So to fully reject the carrier, but message has to be passed through. So using that, we can directly write this condition. Your 1 by RC, this RC circuit's bandwidth should be greater than omega m so that you pass the message, but you reject the carrier. So from this, we can say FM should be less than 1 by 2 pi RC, much less than FC. So this is a constraint for those RCs from a frequency domain. We also saw how to design it from time domain. Now, one thing we did not discuss is, what about the condition on the modulation index? Will it decode or will it be able to demodulate any signal with any any AM signal with any arbitrary modulation index? So let's consider an FM signal, an AM signal, with modulation index greater than 1. So if you see, the carrier amplitude can go 1 minus mu and 1 plus mu. Those are the minimum and maximum values. Now if your mu is greater than 1, your carrier amplitude can also become negative. What does it mean in time domain is that I have shown here a message signal. What happens is here at this point, the dotted line is the message signal, the carrier amplitude, it's becoming negative. So ideally the carrier signal was going through a positive cycle and a negative cycle, but because your envelope, which is A into 1 plus mu into m hat of t, this has become less than 0. So that's what it means. If your mu is greater than 1, it simply means the envelope itself can become less than 0. If it becomes less than 0, then you will have a phase inversion. So you will have a sudden phase discontinuity here. So you will have the sine wave. So that's what I've shown here. I've just zoomed this region. So you will have a phase inversion in the sine wave. Previously the sine wave would have gone this way, but now if your mu modulation index is less than 1 or less than 1, then you will never have such a condition. Now if I pass this signal through a diode detector, remember it's only going to detect the peaks. So it will only detect this way. It will simply track the peaks, and instead of generating a signal which is shown here this way, it's going to generate a signal which is not exactly the input signal. In fact, the positive signals, the negative values of the input are simply detected as positive values. So it looks like a modulus operation, mod of m of t. So that's what happens here. If you use a diode based receiver, even especially if your modulation index is greater than 1, when the envelope is going negative, you will not be able to detect that. You will only detect it as positive. So that's the problem. You will not detect m of t, but rather what you are detecting using the diode circuit is mod of this. You are not detecting the amplitude envelope. This is not what you want to detect this, but you are not detecting this. What we are actually detecting is mod of this. So a modulus function, the thing about this is that, so what if it is a modulus? The problem with the modulus function is that the phase information is lost. Whether it's negative or positive, we don't know whether if the input is negative or positive, the output will always be the same. So that phase information is lost. So therefore the demodulation will be inaccurate. Okay, so that's the problem with having a modulation greater than 1. And a diode receiver is the simplest receiver. You just have a diode and resistor and a capacitor, and it perfectly demodulates your transmitted signal. The receiver is extremely simple, but it comes with a caveat that your modulation index mu should be less than 1. You have to satisfy this condition for the diode receiver to work properly, because what it is actually detecting is mod of AC into 1 plus mu into m hat of t. This is what it is detecting, not the negative of it, but the mod of this. But if you ensure this inside term is always greater than 0, AC into 1 plus mu into m of t, m hat of t is always greater than 0, then mod of x will, I'm just ensuring x always lies in this region, then it will look like a linear receiver, a linear down converter or a demodulator. Okay, so we don't have a problem if it is always greater than 0, and for you to satisfy that condition, for that to be always greater than 0, mod of mu should always be less than 1. Okay, so just to quickly discuss here, what I'm trying to say here is that the diode receiver is an extremely simple receiver, but for it to work, your modulation index mu should be less than 1. And a lower mu, if mu is less than 1, then we know the transmitter efficiency goes down significantly. The lower the modulation index, the lower will be your transmission efficiency. So you're wasting a lot of transmitter power. But you have to keep this in mind, that this was something that engineers were working in early 1900s, where transistor technology has not evolved so much. So therefore they have to keep the radio receivers extremely simple. The radio receivers, most of the radios were mostly receiving circuits. They couldn't transmit. Most of them were receiver circuits. You just had a bank of capacitors. You could tune them. You will receive the intended base station, which was just a narrowband signal. And then you had the typical diode receivers, a diode detector, envelope detectors. And for them to work properly, you needed this condition. But they made, even though your transmitter power was getting wasted, because the receiver became so simple, and in those days simple receiver is less complex receiver means less expensive receiver, because there were fewer components and less bulkier in size. So in those days, before transistors, BJTs and MOSFETs were invented, vacuum tube amplifiers were quite bulky in size. So you needed an amplifier and a diode rectifier. A diode was also realized using vacuum tube diodes. Vacuum tube amplifier, two-terminal vacuum tube diodes were very common. So the more amplifying devices you had in your receiver, the more complex, the more bigger it became in size, and that was not something was preferred from a business decision point of view. So therefore they were ready to increase the transmit power because the transmitter power was several thousands of watts, and so that they can make the receiver extremely simple. But now the question is, with advance in technology, with the invention of transistors, as the transistor sizes became smaller, we could pack more complex functionalities into a smaller space. Once that can happen, can we resolve this issue? Can we solve this problem of wasted uh, or wasted transmitter power in transmitting the carrier signal, or poor efficiency of the transmitters of the first generation radios? And the answer is yes, and we will discuss that in the next lecture. So we could make the receivers more complex so that the transmitter power could be reduced. And all those things, these evolutions took slowly. With the invention of transistors, BJTs, it could be done. You could make the receivers much more simpler, compact in size, and low power. So therefore, we could get away with this problem of modulation index being less than 1. Thank you.